Cruising at 30,000 feet, a commercial jetliner operates far beyond the immediate line of sight of the ground. Relying exclusively on land-based radar requires high-latency relays that cannot always provide the millisecond-level precision required for immediate collision avoidance. To maintain safety in crowded corridors, the aircraft themselves must communicate directly with each other, establishing a localized network that functions independently of ground-based infrastructure. To address the risks of mid-air encounters, the Federal Aviation Administration developed and mandated an onboard solution for commercial aircraft. This system is known as the Traffic Alert and Collision Avoidance System, or TCAS. TCAS functions as an active electronic suite, constantly interrogating the transponders of nearby aircraft to maintain its own real-time surveillance data. By moving the processing power required for collision avoidance from the ground directly into the cockpit, the system ensures that every commercial plane acts as an autonomous surveillance node. The baseline surveillance mechanism scans for threats by transmitting radio interrogations exactly once per second. To guarantee absolute spherical coverage, the transponder utilizes top and bottom antennas, casting a complete signal field above and below the aircraft. These continuous pulses search the surrounding airspace, triggering a specific electronic reply. This communication loop operates on standardized radio bands, with the system transmitting and receiving across the 1030 and 1090 MHz frequencies. This relentless 1 Hz pulling creates an invisible sensor bubble around the aircraft, providing a constant stream of positional data. To avoid a collision, the onboard computer must derive 3 distinct spatial variables from every radio reply. The first variable is range, or physical distance, determined by measuring the exact elapsed time between the transmission and reply. Determining altitude requires reading barometric data provided by the intruder, transmitted as a digital code. The final variable, azimuth, is the bearing of the target relative to the nose of the plane, obtained by a specialized direction-finding antenna. By combining time-of-flight physics, encoded barometrics, and directional geometry, the system independently builds a complete 3-dimensional map of the surrounding airspace. This map illustrates the core logic of threat assessment. Static distance is less important than velocity and direction. The system focuses on the closest point of approach, or CPA, the moment where the flight paths come nearest to one another. If a target aircraft breaches the outer boundary, 45 seconds from CPA, it enters a caution state. This triggers a traffic advisory. The pilot is alerted, allowing them to visually search the other aircraft. If the encounter closes to within 30 seconds of the closest point of approach, it becomes an immediate hazard. Crossing this 30-second threshold forces TCAS to issue a resolution advisory. At this stage, the system shifts from simply alerting the pilot to commanding specific actions based on the collapsing seconds remaining to avoid impact. A resolution advisory provides a maneuver command, instructing the pilot to fly up or down to resolve the conflict. However, if both aircraft independently perform the same escape maneuver, such as both diving at once, the collision remains inevitable. To prevent this conflict, TCAS-2 systems utilize a specific hardware component, the Mode S transponder. The Mode S data link repurposes standard surveillance frequencies into a rapid machine-to-machine connection. Once a second, the planes exchange coordination interrogations, communicating their intended maneuvers over the data link to ensure their paths diverge. This dialogue guarantees that the aircraft execute opposite vertical maneuvers, such as one aircraft climbing while the other observes a descent restriction. This process turns a resolution advisory into a deterministic negotiation, forcing a mathematical resolution that ensures survival. The FAA categorizes this equipment into 3 distinct classes. By combining fundamental physics with high-speed autonomous negotiation, TCAS successfully decentralizes safety, ensuring that every aircraft possesses the tools to protect itself in the sky.